In this video, we'll explore errors in hypothesis testing. First, it's important to understand that errors are possible, even when we don't do anything wrong. Mainly, we have to keep in mind that our sample data provides mere estimates of the broader population features. Inherently, there's error in these estimates. Thus, errors are also possible in the confidence intervals and hypothesis tests that we build from these estimates. For example, we've learned that roughly 95% of samples will produce 95% confidence intervals that cover the population value that we're estimating. Thus, there's a 5% chance that our sample produces a misleading interval, or an error. Similarly, errors are possible in hypothesis testing. Though things aren't so binary in practice, there are two general conclusions that we might make about the population using our sample data. Either we conclude that our results are not statistically significant, or that they are. That is, our hypothesis test conclusions either rule in favor of the null hypothesis or the alternative. Our hope is that these sample conclusions coincide with what's actually happening in the population, where, again, to simplify to a binary, either the null or the alternative is true. For example, if the alternative hypothesis is actually true and our sample provides statistically significant evidence in favor of this hypothesis, then our sample conclusion is correct. Similarly, if the null hypothesis is actually true and our sample does not establish statistically significant evidence to the contrary, then our sample conclusion is correct. However, the other two possible outcomes here correspond to errors. First, suppose the null hypothesis is actually true, but our sample data provided evidence in favor of the alternative. This false positive is also referred to as a type 1 error. Similarly, suppose the alternative hypothesis is actually true, but our sample data didn't establish statistically significant evidence for this hypothesis. This false negative is also referred to as a type 2 error. Let's consider these concepts in the context of an example. Most homes and buildings have a radon detector that's consistently testing the null hypothesis that no radon is present versus the alternative that radon is present. In this context, a type 1 error, or false positive, occurs when no radon is present, but the alarm accidentally goes off. That is, the null hypothesis is true, but our data provides ample evidence in favor of the alternative. In contrast, a type 2 error, or false negative, occurs when radon is present, but the alarm doesn't go off. That is, the alternative hypothesis is true, but the data aren't able to detect it. Now, which error is worse, type 1 or type 2? The answer here depends upon the context of our analysis and which error has greater consequences. In this case, it's worse for the alarm to not detect radon that's actually there, the consequences being illness, than for the alarm to mistakenly go off when there's no radon present, the consequence mainly being just annoyance. That is, in this context, a type 2 error is worse than a type 1 error. Consider another example. Suppose a person is on trial for a suspected crime. Thus, the jury is weighing the null hypothesis that this person is innocent versus the alternative that they committed a crime. In this example, a type 1 error occurs when the person is actually innocent, but the jury concludes that they're guilty. A type 2 error occurs when the person is guilty, but the jury does not find substantial evidence to that effect. Now, in this setting, which is worse, type 1 or type 2 error? Again, the answer depends upon the consequences. Recall here that our justice system assumes that a person is innocent until proven guilty. Thus, it operates under the assumption that a type 1 error is worse, the consequence being that an innocent person is convicted of a crime that they did not commit. Given the consequences of an error, it's important to ask ourselves how common it is to make an error. Let's start here by examining the chances of making a type 1 error, or a false positive. In general, suppose we're testing the null hypothesis that some population coefficient beta is 0, versus the alternative hypothesis that beta is positive. Recall that to test these hypotheses, we must assume that the null hypothesis is true and put the burden of proof on establishing the alternative. We then must compare our sample estimate of beta to the estimates we'd expect to observe if the null were true. In this case, the central limit theorem suggests that if beta were actually 0, as suggested by the null hypothesis, then the sampling distribution for all possible sample estimates of beta would be normally distributed around this value of 0, with some standard error. With this in mind, suppose our sample estimate happens to be 3 standard errors above 0. By the 68, 95, 99.7 rule, there's only a 0.15% chance that our estimate would be this high if the null were true and beta were actually 0. That is, the p-value for our hypothesis test is 0.0015. The rarity of this event, or the small size of the p-value, indicates that our sample estimate is not consistent with the null hypothesis. Thus, we have statistically significant evidence in favor of the alternative. Next, suppose that our sample estimate of beta were a little less extreme. It's only 2 standard errors above 0. By the 68, 95, 99.7 rule, there's still only a 2.5% chance that our estimate would be this high if the null were true and beta were actually 0. That is, the p-value for our hypothesis test is 0.025. In this case, the relative incompatibility of our sample estimate with the null hypothesis would still lead to statistically significant evidence in favor of the alternative. In general, small p-values like those we've seen here indicate that our sample estimate is not compatible with the null hypothesis. But how small is small enough to reject the null in favor of the alternative? Though it's certainly not a magic rule, comparing the p-value to a value like 0.05 establishes a common guideline. If our p-value is less than 0.05, we'll conclude that our results are statistically significant in favor of the alternative. If our p-value is greater than 0.05, we'll conclude that our results are not statistically significant, thus conclude in favor of the null. But this guideline is essentially saying that we're okay with being wrong sometimes. Mainly, suppose that the null hypothesis ends up being true, or in this example that beta is actually 0. Then we observe here that 5% of samples will produce bigger estimates that happen to fall into the red zone here. These estimates then lead to p-values that are below 0.05. In other words, we're saying by this 0.05 cutoff that we're okay with making a type 1 error 5% of the time. The important point here is this. We control the type 1 error rate. If we're okay making a type 1 error 5% of the time when the null is actually true, we can evaluate statistical significance by comparing our p-values to 0.05. If we want to be more careful and only make a type 1 error 1% of the time when the null is actually true, then we can evaluate statistical significance by comparing our p-values to 0.01. The point is, we pick. Let's consider a more concrete example. Suppose we wish to model how many correct words per minute a person types, y, by the number of hours they slept the previous night, x. This model is represented by y equals beta 0 plus beta 1x. Using a sample of data, we then wish to test the null hypothesis that there's no association between typing speed and sleep, that is, that beta 1 is 0, versus the alternative that the more one sleeps, the more effectively they can type. That is, beta 1 is positive. Of course, different samples will produce different estimates of this model. For example, suppose that the null hypothesis is true. There's actually no relationship between typing speed and sleep. The picture at right shows 100 different possible sample estimates of the relationship that we might observe in this scenario. Though most of these estimates are relatively flat, around here, reflecting thus the lack of association between typing speed and sleep in the population, some are fairly negative and some are fairly positive. In fact, just by chance, 5% of these samples produce abnormally high slopes, thus mistakenly suggests that typing speed significantly increases with sleep. That is, 5% of the samples produce type 1 errors. Now, whereas we control the chances of making a type 1 error, type 2 errors depend upon a variety of factors, most of them being out of our control. For example, suppose there is a positive association between typing speed and sleep. That is, that our alternative hypothesis here is true. Let's explore some factors that impact our ability to detect this association, hence to avoid a type 2 error. First, suppose that in the underlying population of typists, we observe the following relationship. The effect size, or the slope of this relationship, is actually 2, so beta 1 equals 2, meaning here that for each additional hour of sleep, typing speed improves by 2 words per minute on average, and we can see that in the slope of this blue line. Further, the strength of this relationship is weak to moderate. The typical person's typing speed falls 7 words per minute from their model prediction. Next, suppose we were to estimate this relationship using data on a sample of just 25 subjects. One possible outcome is shown here. In this case, notice that the gray error bars encompass the possibility that there's no relationship between typing speed and sleep. Thus, this particular sample would lead to a type 2 error. That said, checking out one possible sample doesn't provide much insight into the relative frequency of such errors. For example, let's check out 100 different sample estimates of the population model, represented by the 100 lines here. The red lines reflect the type 2 errors, samples that happen to produce slope estimates that were too close to 0. Thus, they mistakenly led to the conclusion that there's no statistically significant relationship between typing speed and sleep. In fact, roughly 60% of the samples here produced type 2 errors. Now, suppose that the strength of this relationship were the same, but the effect size, or the slope, was bigger. For each additional hour of sleep, typing speed improves by 5 words per minute on average, as opposed to 2 words per minute. Now pause here to ask yourself, will it be easier or harder to detect this relationship with sample data? Thus, do you expect the type 2 error rate to decrease or increase? In fact, the type 2 error rate decreases to near 0. The greater the effect size, or the further the actual population coefficient is from 0, the further our sample estimates, or sample coefficients, will tend to be from 0. In turn, the further the sample estimates are from 0, the easier it is to detect a significant relationship. Now, suppose that we keep the effect size in the population at 2 words per minute for each hour of sleep, but that we increase the strength of the relationship. The typical person's typing speed falls only 2 words per minute, not 7 words per minute, from their model prediction. Pause to ask yourself here, will it be easier or harder to detect this relationship with sample data? Thus, do you expect the type 2 error rate to decrease or increase? In fact, the type 2 error rate decreases to near 0. Essentially, the stronger the relationship, the less error there will be in our sample estimates. Thus, the more consistently these estimates will hover around the actual effect size of 2 in this example. In turn, then, it's easier to detect a significant relationship. Finally, suppose that we keep the exact features in the population, yet we increase our sample size from 25 to 200. Consider just one possible sample outcome in both of these settings. Notice that when we take a small sample of size 25, our error bars here are wide enough that we're not able to detect a significant relationship between typing speed and sleep. In contrast, though the estimated slope of the larger sample size 200, This slope is similar to that in the smaller sample. The increased sample size, however, leads to much smaller error bars. With less error, we are able to detect a relationship between typing speed and sleep. Notice that when we repeat this process a bunch of times, the type 2 error rate is roughly 60% for samples of size 25 and drops to near 0 for samples of size 200. In conclusion, let's reflect on some key observations about hypothesis testing errors. First, we control the type 1 error rate. For example, suppose we compare our p-values to the non-magical threshold of 0.05, a threshold that we pick. Then if the null hypothesis is actually true, 5% of possible samples will mistakenly reject the null in favor of the alternative. In contrast, the type 2 error rate depends upon a variety of factors. We observed that when the alternative is actually true, it's easier to establish statistically significant results when the effect size is large, that is, when the actual population coefficient is far from 0, when the strength of the relationship in the population is strong, and or when we have a large sample size, hence smaller errors. Unfortunately, we have less control over the factors that influence type 2 errors. If we really wanted to avoid type 2 errors, we have a couple of options, in theory at least. We could make it easier to establish statistical significance, hence decrease type 2 error, by increasing our p-value threshold from 0.05 to say 0.1. However, this would also lead to an increase in the type 1 error rate. Or we could take a larger sample size. However, this is easier said than done. Data collection is often a time-consuming, costly process.